Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. As a research computational mathematician of the 1970s and 80s that executed supercomputer calculations from Corvallis, Oregon, United States to Los Alamos, New Mexico, United States, I believe that there are more mathematical equations to be yet discovered. I believe that there are partial differential equations beyond the blackboard that has never been scribbled on the blackboard. For that reason, my quest for a new internet was motivated by my need to execute the fastest mathematical computations and to execute the fastest companion email communications that must arise while executing those computations across my ensemble of 65,536 processors that defined that new internet. That quest for the fastest mathematical computations and email communications was preceded by another quest for the correct system of coupled nonlinear and time-dependent partial differential equations of modern mathematics and extreme-scale computational physics. Those partial differential equations defined the initial boundary value problem of modern calculus that was at the computational testbed for my calculations that I executed across my global network of 65,536 processors that in turn outlined and defined a new internet. That is, I wanted to go beyond recording the fastest computational speeds. I wanted to record those speeds across my new internet. I wanted to not only record speeds that were previously unrecorded, but to record those speeds while solving the correct partial differential equations. Recording those speeds required that I mathematically discover the century-old mathematical error that was unknown to mathematical physicists that formulated the initial boundary value problem of modern calculus that was at the mathematical foundation of petroleum reservoir simulators. To record those supercomputing speeds required that I invent the correct partial differential equations. I invented 36 mathematical terms called partial derivatives that measure changes in velocity both in time and space. Those mathematical terms encoded inertial forces that were not accounted for in the second law of motion of physics and that were not coded into petroleum reservoir simulators. I contributed to modern algebra by inventing 36 partial difference terms of extreme scale algebra and computational physics. Those algebraic terms decoded or discretized the 36 partial derivative terms that I invented. Those terms defined the 9 partial differential equations and defined the 9 partial difference equations that I invented that are called the Emeagwali's equations and that could be used by computational physicists to simulate and enhance the amount of oil and gas that is discovered and recovered. I mathematically discovered that research computational mathematicians of the oil and gas industry should go back to their blackboards and correctly rederive their core equations from first principle or from the second law of motion of physics. The partial differential equation of modern calculus and computational physics should speak its own truth, but it should be a truth that is legitimized in its entirety by the laws of physics that the partial differential equation expressed. I mathematically discovered that computational physicists did not correctly derive the system of partial differential equations of the calculus of petroleum reservoir simulation. That system of partial differential equations governs the subterranean motions of oil, water, and natural gas that flows from a water injection well to an oil and gas production well. The incorrect partial differential equations in computational physics textbooks of the petroleum industry is classified as parabolic. However, I correctly rederived and reclassified them as hyperbolic. The incorrect system of partial differential equations in textbooks on porous media flow do not point to an actual problem. Do not point to the incorrect system of partial differential equations in textbooks on porous media flow do not point to an actual initial boundary value problem of modern calculus. In reality, the incorrect system of partial differential equation in calculus textbooks detracts from the true initial boundary value problem that gave birth to it. The partial differential equation must abstract from the problem that it governs, not the problem defined by the partial differential equation that governs it. For that reason, the 36 partial derivative terms that I invented were abstracted from the oil, water, and natural gas that were in motion a mile deep and across the petroleum reservoir that is being simulated. The 9 new partial differential equations that I invented were beings of reason, but what they simulated were real beings. The reason I make this distinction between beings of reason and real beings is because I am often asked, did you discover or invent Emeagwali's equations? I answered that to discover or to invent is to see something or to see an equation that was previously unseen in any calculus textbook. The answer is that I discovered the Emeagwali's equations. If my partial differential equations existed in textbooks of modern calculus, and that I invented the Emeagwali's equations, if my partial differential equations did not previously exist in calculus textbooks. I am the computational mathematician that contributed to the partial differential equations of the calculus that is used to discover and recover otherwise undiscoverable and unrecoverable oil and gas. I contributed to modern mathematical knowledge by mathematically discovering how to accurately derive the correct system of partial differential equations of a new calculus and of computational physics simulations that governs the subterranean motions of oil and gas. I correctly classified those partial differential equations as hyperbolic. I corrected those critical errors when calculus textbooks incorrectly classified them as parabolic instead of hyperbolic. My mathematical contributions, that is the new algebra that were at the foundation of extreme scale oil and gas simulations, was headline stories within the mathematics community, as well as the cover story of the May 1990 issue of the Siam News. The Siam News is the top news journal of record in the field of mathematics. The Siam News is published by the Society for Industrial and Applied Mathematics. In the May 1990 issue of the Siam News, I explained to research mathematicians that my diagonal matrix that had 24 million by 24 million, mostly zero entries, was a world record in extreme scale algebra of 1989. That diagonal system of equations of algebra allowed for a ruthlessly pared down computer code. I used emails to distribute my 65,536 computer codes to my ensemble of 65,536 commodity processors. Those processors were identical to each other. Those processors were equal distances afar and apart from each other. Those processors were the building blocks of a new supercomputer. Those processors outlined a new internet that I visualized as encircling a globe in a 16-dimensional hyperspace. Each processor was my metaphor for a computer that was at a node within my global network of 65,536 processors and was my small copy of the internet.
Insightful and brilliant lecture.